Okay.
One minute.
1 minute late. Okay, I think we can deal.
Good afternoon, everybody. Welcome to our TTP. Today's presentation will be given by Mark. It's about subqueries, Unnesting arbitrary queries, right?
Yes.
And well, Mark, the stage is yours.
All right, thank you. Yeah, so we've kind of decided to merge the reading club and the TTTs. So this is not my work, it's a work by Neumann and Alfons Kemper. But I will present it anyway, and I've been working a lot with this because I've been actually implementing this paper into DuckDB. So I would say I have studied this work quite in depth. So yeah, to start off with, I will ask, what is a subquery? For those that are not familiar, I hope that's 0 people here. Basically, SQL allows for subqueries inside arbitrary expressions. And from a user perspective, this is very powerful. Suppose that we want to, for example, find the student that has the highest score in our students table. We can use a subquery where we, in the where clause, compare the score of the student to the maximum score from the student's table. This is an example of an uncorrelated subquery. And this is, from a user perspective, very easy to write, quite easy to reason about. However, from a systems perspective, it's a bit of a nightmare because it basically means that you can have these arbitrarily nested subqueries. And actually, this is a simple case. It gets worse because you also have correlated subqueries. And in this case, you can use columns from outer tables inside the subquery. So suppose we want to rewrite our previous example, and we want to not only find the highest scoring students, but we want to find the highest scoring students per major. We can then use the following subquery where we use a column from the outer table inside the subquery. And the way that you can kind of envision how this should work is that the subquery is kind of like a function that takes as a parameter the correlated subquery, the correlated columns. So this is a correlated subquery. So logically, these subqueries, they're supposed to be executed once for every row. So as an example, let's resolve the queries using this table, fictional table. The names are not chosen to represent anyone in particular. We have here the names Tim, Pedro, and Abe, who are doing the majors, computer science, math, and have a score of 9, 8, and 10, respectively. So if we go back to our uncorrelated subquery case, we're supposed to execute the subquery once for every row, at least logically. So we get the max score of the students, which is 10. We compare against the current score of Tim, which is 9. The row doesn't pass. Go to the next row, 8, again, not equal to 10, doesn't pass. Next row, 10 equal to 10, yes, it passes. So in our result set, we now have Abe. So this is the easy case because the max score basically never changes. It's an uncorrelated subquery. We could just execute this query once, keep the result, and cache it, and then we're good. However, let's try now the correlated case that we discussed before. So we have this query now, and here the major gets, the correlated query gets replaced by the value that it has inside the column. So here we get the max score for all the students that have the CS major. In this case, this is 9. So now Tim passes and gets put into the result set. Next query, Pedro has a score of 8. 8 is not equal to 9, so that doesn't pass. Now we go to Abe. Abe has a 10. However, this changes again because of the major changing. So this becomes 10 again. Abe gets added to the result set, and this is now our result. So now this is a difficult scenario because the max score changes depending on the major of the student. So we can no longer simply cache the result. We can run the query once per tuple, but this is very inefficient. Especially imagine this can be any query. This can have joins, anything. Suppose you have like 3 joins in here. You run it on a table with 6 million rows. You're executing 3 joins times 6 million. That's 18 million joins. That's a lot of joins. You don't want that. So can we do better? Well, what most systems do, or at least tend to do, is that they use heuristic rewrite rules to flatten these subqueries. So for example, our previous subquery, it can be rewritten into this, where we do an aggregation group by the major, and then we do a simple join between these 2 tables. And this allows us to resolve this, this case without having to resolve the whole thing for every single tuple. But not all subqueries are so easy to rewrite. And that the result of these heuristic rewrite rules is that the queries that are rewritten are fast, but the queries that are not rewritten are slow. And slow can mean jump in execution time from seconds to hours. And sometimes just changing a small part of a query can remove the ability to rewrite. Not only that, but it's also just a mess. So here's the list of subquery flattening rules from SQLite. Otherwise a very elegant system. Now suddenly has like these 24 rules that have like been relaxed in 2005. They've been like messed with because they found tons of bugs with this. It's very error prone. And this is just SQLite's list, you know, imagine Oracle's list. It's probably much longer. So basically, this is not what we want. We want to flatten arbitrary subqueries. So that's what this paper is about, how to do that. So before I will go into that, I will first talk about the types of subqueries. And I will only consider the subqueries in the expression subqueries. You also have the lateral joins, but they're like kind of a side case. They're quite easy to resolve using the same system. So the types of subqueries we have is that we have a simple scalar subquery. That's the one we saw before, where every subquery returns one value for every tuple. We have the exist subquery that basically checks for existence. So is there anything that matches, any matching tuple? We have the in clause, which takes an extra column or expression and checks, does anything inside this match with this column? Is it equal to the column? Then we have the any comparison, where you can do any sort of comparison, any sort of equality. You can do greater than equal, which checks, is this column greater than any column inside this right set? And we have the all comparison, which checks, is this column equal to all entries in the set? So to like make it a bit more clear, I will show some subqueries with this following table. Very simple table, 4 rows, 1, 2, 3, null. This table we will use throughout the talk, by the way. I've used it in all of my tests, so it's my favorite table. Okay, so let's show the scalar subquery. Very simple case, we want to select I and I plus the minimum of I from integers. So the minimum of I from the integers, it's 1 in this case. So we basically do I plus 1. So we get 2, 3, 4. And the semantics of the scalar subquery is if there's 0 values returned, because this does not have to return a value, this becomes null. So in this case, no, it does return a value. However, null plus a value becomes null. But if there's 1 value returns, we return a value. And if there's more than 1 value from the subquery, we throw an error. Unless you're SQLite, then you just take the first value. So we've also adapted this semantics because, well, it's a bit more convenient for the user, we think. The SQLite one, yeah, where we just accept the first value.
What is the first value?
Which is arbitrary.
Which is arbitrary, just arbitrary, unless there's an order. Okay, then there's the exist query, where basically you can have more than 1 value, and it says basically if there's 0 values, this is false. If there's more than 1 value, this is true. So here we do exists, select from integers where I equals I1. So here, there is one tuple that passes, so it's true. One tuple that passes, true. One tuple that passes, true. 0 tuples that pass, because there's no tuple where null that's equal to null, because it's always doesn't pass. So that's false. Then we have in, where if there's a match, it's true. If there's any match inside the set, it's true. Otherwise, it's false. And there's some funky null semantics that I will talk about more in the any and all case, because it's the same null semantics. So here we do a select star from integers where I bigger than 1. So there is no match here, because this set basically returns 2 and 3. So there is 1 is not in the set 2 and 3, false. 2 is in the set 2 and 3, true. 3 is in the set 2 and 3, true. Null is null, because null semantics. I will talk more about that here. The any operator, we can have here any sort of expression again, any sort of amount of values. And we return either, this is a bit funky because it depends on the right-hand side. So if the right-hand side has a null value, so in this expression there's a null value, then if there's a match, it's true. Otherwise, the result is null. So if there's a null value here, the result actually cannot be false. So here we select from integers. If we say I is bigger than any of this list, the whole table. So 1 is not bigger than 1. It's not bigger than 2, not bigger than 3, not bigger than null. So the result is false. However, because there's a null value, it's actually null. 2 is bigger than 1, true. 3 is bigger than 1, true. Null, null. If we filter out the null value, this one becomes false. But this one remains null because the null is on the left-hand side. However, nice extra semantic, if the table is entirely empty, it's always false, even if the left-hand side is null. So this is like a bit of a tricky case. All is kind of the opposite of this. So if there's a null on the right-hand side, it cannot be true. It's either false or null. Once we remove the null, it can be true again. And again, if it's empty, it's always true. So it's kind of the opposite of that. So how can we find that? Well, we saw 5 types of subqueries. Really, there's only 3, because both the in operator and the all operator can be rewritten into the any operator, because they follow these same semantics. So I in is equal to I equals to any, and all, you just flip the comparison operator and put a not around it. And those are identical. So you only have to consider these 3 types. So first, let's consider the easy case, the uncorrelated subqueries. And this is nice because in this case, we don't really need to look at what's going on inside the query. We can flatten it without having to actually consider the individual operators. We can just flatten it regardless. So first, let's look at the scalar subqueries. In our case, we're gonna ignore errors if there's more than one row. So what we do is we just push a first aggregate, we just get the very first value, and returns null. And returns null if there's no value found. And then we combine it with the main set with the cross product. So here, suppose you have this query, select I plus the subquery from integers. This will have this simple plan. You have a sequential scan, you have I plus the subquery. The way we're gonna rewrite it is we're gonna do this. We're gonna plop the subquery here. We're gonna add a limit just for efficiency and a first aggregate. Then we combine with the cross product. And it's important to note that here, the right-hand side always has one tuple. So this cross product basically just glues a column on there. It doesn't actually expand the result set size. And then here we can use this value inside the projection. And this way we don't have to resolve the subquery from inside the expression list. It's now part of the tree and we can optimize it and such. And the nice thing is because this works regardless of what is here, right? It doesn't really matter what's there. It's just a black box, you just push this and it works. Exists is quite the same. You do a count star and the count star is going to be either 0 or 1, and then we just do a comparison on the count star bigger than 1. Easy. Any is a bit more annoying. The answer is to use a mark join, and I didn't come up with this name. Neumann came up with this name. Basically, the mark join is a simple explanation is that it just marks the tuples to whether or not they have a join partner. So here, we do a mark join, we have an I equal to any. This will become our join predicate here. And the result is mark join is going to be like a marker that says if there's a join, a matching join partner with all the null handling as well. Like it's actually a bit messy to implement this, but
how does it differ from a semi-join?
Because the semi-join discards the result. This actually marks it. So a semi-join, you basically you take only the columns from the left-hand side. Here you put a marker in there. And also you never discard, like the mark join does not change the cardinality of the left-hand side. The output cardinality is always the cardinality of the left-hand side. And basically, because that's also the semantics you want here, right? Because if you have a scalar subquery, this should never change the cardinality. Like if you have 4 input tuples here, this should always have 4 output tuples, right? So that's how we resolve that. Well, however, the main thing is, of course, correlated subqueries, because they are much more difficult. In the uncorrelated case, we didn't need to actually consider the right-hand side. We could just push some operators, merge them, and it would work. But now somewhere in that right-hand side, we need to glue our correlated column. And that's the main part of what this paper is about, is how to flatten those correlated queries. So the way that they do it is that we first introduce a new join, which is the dependent join. And the dependent join is kind of like executing the subquery once for every tuple, in that basically the dependent join says, okay, my right-hand side, I execute one time for every tuple in the left-hand side. However, this is just like the dependent join is more like something we're gonna work with and remove as fast as possible. It's more like to visualize this. So if we have, for example, our old query, you can see we have a dependent join because it's a correlated query. We have a dependent join with a score, and here you can see the correlated column. And this, of course, does nothing from an efficiency standpoint yet, because you still have the dependent join. And our goal is to eliminate the dependent join. So the first observation that they make is that we only really need to execute the right-hand side once for every unique combination of the correlated columns. Because suppose in this case we have CS, CS, and math as our majors. However, regardless of how many tuples with CS we have, we only, the result of the subquery will not change. So if we put CS there, we have 9. If we put math there, we have 10. And that's it. We only need to execute the query twice, once for every unique combination of correlated columns. So the way we can do this is to actually duplicate eliminate this, and then push a duplicate eliminated scan inside the right-hand side, and do a dependent join with that. And then we join that together with an inner join. That's the way we would model this in this model. And here we use the correlated columns as a join predicate. So that's the way we would do that. And then we're going to push this duplicate eliminated scan down into the right-hand side. The reason that we do this from like a higher level is that this duplicate, like the fact that this is a set, makes it much cleaner to push into like an aggregation and such. So we push it down. And the goal is that we don't want to have a dependent join anymore. And the way we can do that is by pushing the duplicate eliminated scan, the dependent join down, until the right-hand side no longer has a correlation with the left-hand side. And at that point, we can just turn it into a cross product, because there's no reason to do this dependent join anymore. And the way that we push it down depends on the types of nodes in the query. So, so the first node that we have is an aggregate. And the way we can push down aggregate is by pushing the correlated columns into the group by. So here the correlated columns is just the d.major, and we can push into the group by like this. So we now group by the d.major. Next, we have a filter. And for a filter, we don't really need to do anything. We can just push it down. And now our right-hand side no longer has correlated columns with the left-hand side. So now we can turn it into a cross product. And then our dependent join is gone. And then, of course, we can further optimize it, turn this into a hash join, and we can even completely remove the duplicate eliminated scan. But that's basically the essentials of this. And maybe to more intuitively describe why this works, is that basically this cross product, normally you would scan this table once for every row, right? You would scan the right-hand side once for every row in the left-hand side. By doing this cross product, you're kind of doing the same thing, but you're just combining everything and doing all of it at once. And now you're computing it based on this grouping that groups it together based on the correlated columns. And this kind of allows you to do kind of everything at the same time without having to do this like step of executing it once. And the nice thing about this is that then you can do a lot of optimizations here that make it better. Yeah, so there's a final optimization where you can totally eliminate the duplicate eliminated scan, because you will see here that the d.major is always equal to major. And that basically means that there's no value here for d.major that's not equal to major. So you might as well not do this duplicate elimination in the first place, which saves a lot of time, because you don't need to duplicate eliminate this side, you don't need to do this join at all, and you can just rewrite it to this, which is much cleaner, of course. So yeah, basically in the paper, they then further describe how we can push the dependent join down into any operator. So for a projection, we push the node into the operator. So here we have the duplicate eliminated scan with a projection, push the d.major in the projection. For a join, depends on if the left-hand side or right-hand side have correlations. The set operations we push in both sides. And the aggregate, we already saw. In the paper, they say you have to push it through by adding it to the group columns, like this. But actually, this does not always work. It does not work if there's a count star with a filter. And also not if you have like a strange expression like sum I is null. And the reason for that is, suppose that we have this query, select count star from students as of major and score equals 10. So we want to basically get a count of the amount of people that have a score of 10 grouped by major. So this is the count we expect, right? We have CS with 0 and math with 1. However, if we do what they say in the paper, what we're going to get is CS null and math 1. So it's like a really nasty sort of thing. The reason for that is that here we have this filter. And here, this filter, only Abe passes through this filter because he's the only one with a score of 10. Which means that CS will never make it into this hash table, which means that here there won't be a join partner for CS, which means this will be null. So the way that I've solved this is by actually doing a left outer join here, again with the hash. And that basically gives you the groups back. Because here you have basically all the groups. And then you can do like a replacement of the null with 0, and then you get the correct result. This I found, by the way, by one of the SQLite test cases. So run the SQLite test cases.
This is not in the paper.
No, it's not in the paper.
Yet.
But they have actually fixed it, because if you run Hyper and look at it, they actually do generate 2 joins for this query. So they have fixed it. But it's in the paper, they just say push in the group by. But in the paper, they also talk about the relational algebra semantics. And I think maybe there they don't have this kind of weird edge case where the count becomes 0 if there's no, like an uncorrelated count becomes 0 if there's no rows instead of null, like the other aggregates. So I'm not sure. Either way, this is a bug that I found by just pushing it into the group. Other stuff that's not discussed in the paper, correlated NEL. We actually need a special type of correlated mark join where we keep a count star and has null for every group. Which basically requires another hash table, a bit annoying. For window functions, we can push correlate into the partition by clause, and top n functions, we can push the correlate into the order by clause, and then using nth value aggregates to get the proper offset value. I have not implemented this yet, though. It's a bit nasty. But Hyper actually has this, so that is nice. Yeah, so one thing that, of course, you don't think about unless you implement it into a real system is binding subqueries. And this is actually something that's very annoying. So what correlated column should be available in a subgroup? Well, a subquery is like a function call, so any column that can be passed to a function should be able to be passed to a subquery, which means that in select clause, it's either an aggregate or a group, or the normal columns. And this can be ambiguous, as we will see. In the where, it's just the normal columns, having is the aggregate or group, order by is anything that can be in the root of a select, and a limit is no correlation allowed. Also, limit probably shouldn't have a subquery in the first place, but Postgres does support it. So the question is, like I said, it can be ambiguous. So how do we bind this subquery? We do a select, and in that we do a subquery where we do a select sum I1.I. So it's a correlated sum. And there's 2 possible results. I would argue both are kind of correct in their own way. So here we pass the sum as to the subquery, which means there will be 1 result, 6. Here we pass I to the subquery, which means this query will be run once for every row, which means the result will be 1, 2, 3, null. So what is correct? I don't know. All I know is...
So can you explain this? So what do we see here?
So here we run a select sum I1.I, in a correlated scalar query, right? And you can rewrite this to either this case, where you pass the sum I1.I to the subquery, in which case the correlation basically happens in the outer query, and the result will be 1 row, which is the sum. Or you can pass the column directly, in which case the correlation happens inside the subquery, and then the result will be 4 rows, because there's no correlation in the outer subquery. So what do the other systems do? Well, basically this. Postgres and SQLite take this approach, Hyper takes this approach. I would argue both are correct in their own way. I don't know about the SQL standard. The SQL standard, the 99 one I read, has shockingly little on subqueries. So I would say both are correct. I do think this approach is a little bit cleaner, because this approach does never allow you to use aggregations of like the outer queries inside the queries. So this approach I like a little bit more. It's also the one I implemented, but it's ambiguous. Anyway, so more fun. Basically, this also means that a bunch of correlated subqueries get different results. So here we can do both a sum I1.I, and it changes as well depending on the database. So this Postgres is SQLite, and Hyper basically passes the group in this case, instead of the sum, which gives it a different result. And if we pass a different column that's not grouped in, then it will work in Postgres. This is also why I like this syntax a bit more, because you can actually do like a sum over a value that's not part of this outer query. And in Hyper, this will throw like an error because it tries to pass in i1.j, which is not grouped by in this case. So yeah, also this is a nice one. In a subquery, we can have like this max i1.i, which is passed to the subquery, and then we can filter on that in subquery. This works in Postgres, but not in SQLite, because SQLite never accepts aggregates in like the where clause, even if they are like correlated aggregates. So also, yeah, great big fun. This like can totally recommend it. Also, this is a nice case where you sum over both a correlated and uncorrelated column. In this case, the aggregation happens only inside the subquery. So basically, you would aggregate in like the deepest query where you have access to all the columns. Great fun. This one, okay. Anyway, basically, this stuff is pretty nasty once you actually want to get it to run like all the stuff. So as part of this, we made a bunch of tests for the different types of subqueries to test our implementation in order to attempt to cover many possible bugs and problems, because there are many. Like this stuff is really nasty once you actually start implementing it. We all run this on this nice integers table, and we have split it into uncorrelated and correlated test cases. Here are the files in case you're curious. In total, there's like 250 queries in total. Good luck. So we also, of course, tried to run it on other systems to see what would happen. And we split the results into these 6 categories. And first, the uncorrelated results. So we actually found bugs in quite a lot of systems. We found a bug in Hyper, we found some bugs in MonetDB, and we found out that SQLite does not support the any and all operators. Well, okay, that's kind of fine. And now Postgres and DuckDB support kind of the same kind of queries. So what types of errors did we find? Well, in Hyper, this gives the wrong result. So if you have like this I small and all, then actually in the select clause, it will give the correct result of null, because null is not smaller than all of this, basically becomes null. But in the where clause, it does actually pass. So you can see here the condition that we replicate here is null, but it passes the filter anyway, which I guess is some optimizer that screws with that. And this is like all the 10 results. These queries time out in MonetDB, so they have like a group on a subquery and a case expression, a sum over a case expression that has a subquery. Yeah, I tried to make these as nasty as possible, of course. These give incorrect results in MonetDB. Here you get cardinality mismatches. So here actually you have a scalar subquery that explodes your table from 4 rows to 16 rows, and here it removes all the rows. And these also have some strange inconsistencies where here the columns are disappearing, and here the not I in gives a different result from the I not in. Basically, this stuff is difficult. There's a lot of like pitfalls here, and I've hit a lot of bugs with that. Next one, the correlated subqueries. These are even more difficult, and actually the biggest surprise was that I found a bug in SQLite that I did not expect at all. So I found 2 incorrect queries with Hyper and 2 crashes with Hyper, which actually corrupted the data. So big I. PostgreSQL does not support one query, which is a full outer join within a query on correlated columns. And Hyper actually did run that query, so props to them. We also don't support all the queries yet because we don't want to support the order by and the limit yet. We're not there yet. And MonetDB has some problems, yeah, especially the binder errors. I made a different category here for the binder errors because a lot of queries in MonetDB don't pass the binding when they should. Like they say, like the column is not there, but it's there. So all the systems would run it, but MonetDB would throw this binder error. There's also some more timeouts and some incorrect results. So this is the SQLite bug. It's very like not that big a deal. Of course, because if it was a big deal, it would have been caught. So if you have a query that has a limit 0, of course it should pass just a null value everywhere, right? Because it cannot possibly return rows. However, in SQLite, it actually returns the rows. It kind of ignores the limit. So kind of benign, but it is a bug, and it's also on the latest version of SQLite. So yay, defeated the master. This is the one that has the incorrect result in hyper, in the same query, but with a limit 1. So then actually, instead of the limit 1 in this query, it's a scalar subquery, should not change the result at all. However, in hyper, they kind of push the limit and it removes all of the rows but one on the right-hand side. So also kind of benign. And actually, if you add an order by, hyper does do this correctly. So it's kind of like some optimization thing again, I suppose. This is the hyper killer, which is very unexpected because it's not even like that difficult of a query. So this query, if you run it on a table with null values, it gives a segmentation fault and also corrupts the data. So when you load the database again, then the null values get replaced by like this weird 0 that do not match the I as null, but also do not match the I as 0. So it's, I think, some statistics bug, if I had to guess. I don't know. Either way, very strange story. This is the one query that PostgreSQL does not support. Also, Hyper does not. Also, SQLite does not support it. Hyper does run it. It's basically a full outer join on these two tables inside the subquery, where you use the correlated column inside one of the join conditions. That one Postgres does not like, but it does not do it wrong. It just doesn't support it. And Hyper does run this beautifully. Yeah, so this is what we don't support in DuckDB yet, order by limit or offset, and the full outer join as well. And yeah, these are the binder errors in MonadDB. So here, this is kind of what I was talking about, where here this column is clearly there. Here this column is clearly there, but somehow it can't find them. We also have like a different category, unexpected errors. That's kind of like errors like this, where it's not a parser error, but you have like a strange error like subquery result missing, or relational query without result, or error in optimizer. So yeah, those that fall under unexpected errors. Then these time out again in the correlated case. So this one, the nice order by a correlated subquery is nice. The sum inside a sum, this throws an error in most systems, and some set operations inside inside subqueries. So subqueries, yay! So that was the talk. I don't have a conclusion slide. I just realized. I hope that was informative. It's been like a month working on this. It's difficult to get right, shall we say.
Thank you, Mark. Does anyone have a question?
Yeah, you mentioned that for a specific correlated subqueries you need a special variant of the mark join. Can you elaborate on that?
Okay, so if you have a mark join, maybe I'll write on the board.
Let's talk about mark join.
Yes, okay. Of course, like I'm supposed to be an expert on this. So, I should not have done. So basically in the mark join, you have like an any or all predicate, which means that if you have null with an empty set, it should return false instead of null. And if you have like a value with a set that has a null value, it should return null instead of false. So basically, you need to know if on the right-hand side there's a false or a null. It's an empty set or it's a null value. In the uncorrelated case, this is easy because you just run the query once and there's either a null value or there's not. But in the correlated case, you need to know this basically per correlated column. So you need to have like a hash table that says like, okay, if I have null on my correlated set, then I have 0 results and I have 0 null values. Like I keep like a count of the value you're comparing against, because that kind of accounts for the null value. So if you have 1, then you have 2 results. One of them was not null, and then you know you have a null value for this one. You know you have an empty set for this one. So basically, that you need to have like an extra hash table for that to do that correctly. Yes.
Great work, good. So we're now to wrap up. So when are you going to add actually the correlation actually directory to the MongoDB test web?
That is
Otherwise, actually somebody else had to spend another 2 weeks to decipher your code. Well, you have it all available, so I
this
would
is-
expect actually MongoDB/test/correlation and there are 256 or whatever of its queries.
Well, I would say that is quite easy to do with like a simple script. All the tests have their answers right there.
Okay, so I appreciate if you finish that by tonight.
Tonight I don't have that much time, but we can look into it. We can talk about it.
Well, it's not talking, it's not a question. So just wrap it up.
Okay,
Because
we'll see about
that
that.
actually makes it easier actually also for others to like Niels to fix.
Maybe Alex and Pedro have some time.
Yeah.
But they are pretty doing other things.
Well,
They are fixing other bugs of the same group. What are the right stuffies?
I also think thinking of the camera. But I have a question. Why do those query fuzzes like SQL fuzz they don't generate these kind of queries?
Well, they might not. I
So
mean,
some of them actually indeed are generated by the generator. They can be. I have found a number of actually things, endless recursions actually were found that way. But by randomness, it could take actually a couple of 100,000 randomly generated queries before you find this one. This is a more organized exploration of the space.
Also, one of the problems is that, of course, like if you run a fuzzer, there's gonna be queries that are supposed to give errors, right?
Yes.
So you don't know. You get like a query and you think like, okay, it shouldn't work. However, like things like this, you wouldn't catch because yeah, this query should work, but it doesn't. It throws an error. But if you run a fuzzer, you don't know that. It's a query that throws an error. You probably just not look at it anymore. Or you also don't know the answers. So if you have like incorrect results like this, then you would also not think about it. Basically, you would say like, okay, it works, it runs, I have a result, great. So those cases you would not really catch with a fuzzer. The timeouts, yeah, you can catch. This you can catch. Or the crash as well. Those you
Crashes
can catch.
mostly. Single Smith actually was mostly actually to find crashes.
Yeah,
Anything actually beyond that was hardly possible,
yeah,
given the amount.
yes.
From your deep insight into subqueries, would you say there's any hope for the heuristics approach?
I would say it's quite a waste of time. Like there's no reason to do it, and it's so much work, like so much rules, so error prone. Like I would say, why would you do it when you have this, basically? Because these kinds of queries, like the base plan that it generates, like this, with the cross product, is not so efficient. But optimizing this into a good plan is very easy. In a lot of cases, and then you actually get like proper support. Even if it's not optimized, it's still much faster than a case where you just actually run it like naively.
And a quick follow-up.
Yeah.
There are no queries that you cannot fold, basically.
Well, the order by I don't exactly know completely, but basically, yeah, there's nothing that you really can't fold.
Any more questions? So, thanks, Mark. Yeah.
Thank you.